Water molecules are incredibly stable. Their oxygen and hydrogen bonds are tightly locked, and breaking them to extract pure hydrogen requires immense physical force. This thermodynamic curve plots temperature against water dissociation. Using direct heat to split water yields almost nothing until the temperature exceeds 2,500 degrees Celsius. Standard industrial heat sources max out far below that threshold, typically operating between 300 and 1,000 degrees. We cannot simply build hotter reactors to reach that 2,500-degree mark. At those extremes, the advanced metals and alloys required to physically construct the containment vessels begin to melt. This severe thermal deficit forces industrial hydrogen producers to rely heavily on fossil fuels, extracting hydrogen directly from natural gas instead of using clean heat to split water. Because direct thermolysis is physically inaccessible, producing clean hydrogen at scale requires a scientific workaround to bridge a massive temperature gap. On June 26, 2026, scientists at the Indira Gandhi Center for Atomic Research in Kalpakkam, Tamil Nadu, activated a new infrastructure project. This full-scale industrial complex is physically integrated into the active nuclear site, designed to prove the process can operate at utility scale. The facility extracts pure hydrogen by utilizing direct heat from India's fast test reactor, producing zero carbon emissions in the process. But the fast test reactor operates at a maximum temperature of roughly 550 degrees Celsius. Compare these metrics. The left shows the 2,500-degree requirement for water splitting. The right shows the Kalpakkam reactor's 550-degree output. Despite this massive deficit, the facility bypasses the electrical grid entirely, never converting that heat into electricity. The reactor is merely 2,000 degrees too cold to split water, and the process uses no electrical current. Yet hydrogen is flowing. The standard method for producing zero-emission hydrogen is electrolysis, which relies on electrical current to shock water molecules apart. This flow diagram illustrates the traditional pathway. Nuclear heat boils water into steam, generating electricity that runs the electrolysis. At both the heat-to-steam and steam-to-turbine stages, massive thermal energy bleeds out. Transmission lines and electrolysis cell resistance introduce further inefficiencies, leaving only a fraction of the starting energy as extracted hydrogen. Converting thermal energy into electrical energy discards more than half of a reactor's total power potential before a single water molecule is touched. A thermochemical cycle offers an alternative. It uses direct, raw heat to drive a sequence of chemical reactions, bypassing turbines and generators entirely. To maximize hydrogen yield, BARC engineers bypassed electricity entirely, instead using a multi-stage chemical cycle to overcome the water molecule's stability. They engineered a specific reaction sequence known as the copper-chlorine thermochemical cycle. This flow diagram shows a closed-loop architecture. Water and heat enter, hydrogen and oxygen exit, while copper and chlorine compounds cycle continuously, acting as catalysts without being consumed. In the first node, hydrolysis, 400-degree reactor heat initiates the cycle, forming copper oxychloride and hydrogen chloride gas. At 500 degrees in the second node, copper oxychloride splits, expelling pure oxygen out of the loop. This 500-degree peak sits safely within the reactor's limits. The cycle continues through the third and fourth nodes. At lower temperatures, the remaining compounds react, isolating and releasing pure hydrogen gas. In the final leg, the residual copper and chlorine compounds recombine, returning to the first node to begin the sequence again. The process isolates hydrogen and oxygen perfectly. Zero carbon dioxide or greenhouse gases are produced at any stage of this cycle. The copper-chlorine cycle does not magically reduce the total energy required. It divides the monolithic 2,500-degree thermal barrier into 4 manageable steps that a 550-degree reactor can comfortably clear. The Kalpakkam facility takes this theoretical chemistry out of the laboratory, operating as a physical, full-scale technology demonstrator. This success relies on 4 decades of high-temperature operations from India's fast breeder test reactor program. The primary engineering challenge of scaling this process is moving intense heat from a highly radioactive core into a volatile chemical processing plant without risking contamination. This 3D schematic maps the solution. The nuclear core on the left sits physically isolated from the chemical plant on the right, separated by a closed-loop liquid sodium heat exchanger in the middle. Heat flows from the core into the liquid sodium, and the sodium carries that heat to the chemical plant. The radioactive coolant never touches the hydrogen process. Driven solely by this clean thermal energy, the chemical plant pipes pure hydrogen directly into industrial storage. Integrating a nuclear core, a liquid metal heat exchanger, and a closed-loop chemical plant proves that direct heat hydrogen production is viable at an industrial scale. This infrastructure introduces a concept called energy decoupling. Heavy industries no longer have to rely on grid electricity to source their clean hydrogen. Operations that require massive chemical inputs, like heavy steel manufacturing and ammonia-based fertilizer production, can integrate direct heat hydrogen seamlessly. Developing this technology domestically allows India to bypass expensive imported electrolyzer hardware and build its own production networks. By optimizing the cycle for commercial scaling, Kalpakkam is establishing a precise engineering blueprint for nuclear hydrogen extraction. By combining atomic physics with closed-loop chemistry, engineers have secured a continuous, zero-emission fuel supply without straining existing power grids. The Kalpakkam facility establishes a direct physical bridge between atomic energy and heavy industry, eliminating the carbon deficit at its source.